G'day. Here's a little puzzle. I've drawn a square and added a dot to each corner of the square. So I've got 4 boundary dots right now. Let me add some dots inside the square. Maybe we'll add 2 dots. 1, 2. Great. Now what I want to do is actually connect pairs of dots with straight line segments and subdivide that square into triangles. For example, we're going to do something like this. Line segment, line segment, line segment, line segment, line segment, and there. I've subdivided the square into triangles. But I have a rule. Every triangle I make has to have exactly 3 dots on its boundaries, 1 at each corner. So this triangle's fine. It's got 3 dots on its boundary, 1 at each corner. That's fine. That's fine. But this triangle is invalid. It's got more than 3 dots on its boundary, and I could fix it up by drawing some more line segments. I'm going to draw this one here and that one there. Great. Now every triangle is valid. I've got a lovely subdivision of the square into triangles. And how many triangles do I have? I see I have 6 triangles. All right, so when I drew the picture that time, I subdivided the square into 6 triangles. Let's do it again. Let's do it a different way this time. So the 4 dots on the corners of a square. Let's add 2 more dots inside the square. Maybe we'll do them like this time. And let's subdivide the square into triangles. Here goes. Maybe we'll do this. Maybe we'll do this and do that. I think I'm getting a different picture this time. I'm going to do this time and that. All right, and how many triangles do I have this time? I have 3, 2, and 1. I have 6 triangles again. In fact, try it. Draw a square, 4 dots at each corner, put 2 dots anywhere you like inside that square, make triangles as many as you can, small as few as you can, and I bet you cannot escape 6 triangles. Whoa, whoa. In fact, that begs the question, what if I change the number of dots I put inside? For example, here's a square. What if I put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots inside that square? Connect them with line segments, make triangles. I bet your bottom dollar you'll end up with 22 triangles no matter what choices you make. What's going on? Is there something special about squares? Can I do this with like a 17-sided shape with 400 dots in the middle? Try it out. Is the number of triangles we create invariant? Back in the 1600s and 1700s, mathematicians started noticing something amazing about the types of diagrams they were drawing. And these ideas were brought together by Leonard Euler in the mid-1700s. Now, we've been drawing a diagram with dots. We had 4 dots at the corners of the square, and we added 2 more dots inside the square. People tend to call dots vertices, V for vertices. Then we connected pairs of dots as straight line segments. People tend to call those edges, E for edges. And then we created some regions. All the regions we created were triangular regions. So we have R for some regions. Great. Now, here's a more general diagram just of that type. I've definitely got some dots. I've got some vertices. In fact, I can see here I've got 4, 3, and 2. I've got 9 vertices in that picture. Now, my edges here are a little bit looser. They don't have to be straight lines. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. Actually, this one's kind of curious. It's an edge that connects back to the same dot. That's allowed. So in this picture, I've got 10 edges. Now, I'm definitely creating some regions. I've got 1, 2, 3, 4 finite regions. But I'm also going to count the big unbounded region around all that. So I've actually got 5 regions in that picture. Great. And I see this picture actually comes in 3 basic disconnected pieces. It's got 3 components, 3 separate components. C for components, 3 of them. Great. And Euler's formula says that V minus E plus R is sure to be 1 more than the number of components. And let's check that. I see V plus R, that's 14 take away 10 is 4. Basic arithmetic is my word. So 4 on the left-hand side, and 1 plus 3 is 4. 4 on the right-hand side. Yes, that formula is working for this particular picture. Wow, great. All right, so the thing is, that formula is going to work for all such pictures you draw. And let me see if we give sort of an intuitive reason as to why that would be the case. And how I'm going to do that is basically, well, first of all, remove this part I don't need. Let me redraw this picture, but let's start by stripping away all the edges. Let's just go with the dots. I've got some dots here. I'll do it in pink this time. I've got 4 dots, 3 dots, and 2 dots. So let's just do that basic version of the picture with all the edges gone. So how many vertices do I have? I still have 9. That's still the same number there. Number of edges, no edges. Number of regions, number of regions is going to be the big unbounded region. And what's interesting, on the right-hand side, I'm going to have a 1, because there's a 1 there. But how many components do I have? Well, each vertex is its own component. So actually the number of components equals the number of vertices. It's going to be 9 again. But it is 9. There it is. Voila. Any picture that's just dots, I can see this formula is sure to be balanced and correct. All right, so I know if I just got dots on the page, nothing more, we've got a correct formula. Now let's start adding edges in, one at a time. So let me remove this so I can make it a little clear what's going to go on. Let me add, say, this top edge here. Oh, I've definitely added an edge. Edges went up by 1. Great. But what have I done? I've actually connected two separate pieces, two separate components. The number of components has gone down by 1. That's gone down by 1. And fortunately, there's a minus sign there. So on the left-hand side, we went down by 1. On the right-hand side, we went down by 1. The formula's balanced. It's still true for this picture. Great. But I even connect this edge. I can see the number of edges go up by 1. The number of components has gone down by 1. But thankfully for that minus sign, I can see everything's still going to be balanced. So whenever I connect two components, I can see the number of components is going to go down by 1. Number of edges is going to go down, up by 1. But that minus sign is handy. Great. What's interesting is when I draw an edge that connects from one component back to the same component, like that. Okay, in that case, yes, I've drawn another edge, that's for sure. I've not changed the number of components this time. The C doesn't change, but I have created a region. The number of regions went up by 1. And again, I can see this formula's balanced. That minus sign means I went -1 there, +1 there, nothing's changed in the formula. Everything's still balanced. Whenever I connect a component back to itself, I create a region. Number of edges goes up by 1. Number of regions go up by 1. Thank you for that minus sign. And so there we go. Connect two different components, not a problem. Components go down by 1, edges up by 1. Connect a component to itself. Okay, nothing changes in terms of the number of components, but the number of regions go up by 1. And if we see, as we rebuild this diagram, everything is staying balanced and correct. Nothing is changing in that formula. It's still a balanced formula when we finally get back to our original picture. Therefore, this formula is indeed holding for our original picture. That's it. There's Euler's formula. Okay, back to our original puzzle. Instead of doing 4 dots to make a square with 2 dots inside, let me now do 7 dots. I think it's 7 dots. 7 dots on the outside, a septagon with 5 dots inside. Okay, so in this picture, I've got the number of boundary dots. B for boundary dots is 7. Yes, that is correct, yes. And I've got 5 inside dots. And what we're going to do now is actually connect these dots, pairs of dots with straight edges, and make triangles. And the question is, how many triangles will we get? And if we play with the puzzle, it seems that's going to be preordained. We have no choice but to get a certain number of triangles. All right, so let me do it. Let me quickly make some triangles so you just watch me have fun making triangles. It's probably not that fun to watch, but here we are, making lots of triangles. Yes, I can certainly count them, but I'm wondering if I can understand why this number, whatever I'm getting, is preordained. All right, so there's a picture of a nice triangulated septagon. Okay, so the way to maybe make sense of what's the formula for the number of triangles just has to be is just count things in different ways. I mean, obviously I want to count the triangles. Okay, but that's the hard part. I've counted the number of dots. Maybe I should count the number of edges now. Okay, let me count the number of edges. How many edges are there? Well, that seems hard. I want to do it abstractly. So what I could do is see if I can reason abstractly then. Each triangle certainly has 3 edges. Each triangle has 3 edges. 3 edges, 3 edges, 3 edges, 3 edges. So actually, each triangle has 3 edges. The number of edges must be 3 times the number of triangles. Done. Well, not done. Well, not done. Because there's a problem with that. This edge here, for example, is double counted. It gets counted once as one of the 3 edges of this triangle, and again as one of the 3 edges of this triangle. This edge here also gets double counted. Once as one of the 3 edges here, and once as one of the 3 edges here. So it seems to be doubling all the edges. Actually, not quite all, because this edge here is not being double counted. It's going to be counted once as one of the 3 edges here, and that's it. So every interior edge is double counted. Every boundary edge is not double counted, it's single counted. So each triangle having 3 edges is actually doing what? It's counting for us each interior edge twice, so I'll get double the number of interior edges. I don't want to use I. Let me do E sub I, edges on the interior. They get double counted, but each boundary edge is actually counted once. And how many boundary edges are there? The same as the number of boundary dots, B, in this case 7. All right, so there's one abstract formula getting us going on how to get a handle on what T has to be. Do we have another formula to play with? And the answer is yes, Euler's formula. The number of vertices minus the number of edges plus the number of regions is 1 more than the number of components. Vertices, how many do I have? Well, I've got B boundary dots and I interior dots. That's all the vertices. Great. Take away the number of edges. How many edges do I have? Well, I just did EI for the interior edges, plus we also have boundary edges, B of them. Great. Equals plus the number of regions. How many regions do I have? Well, each region is a triangle, so I'll have T of them, that's what I want, plus 1 more region, the unbounded one. Plus 1 has to equal 1 more of the number of components. How many pieces do I have? Well, this picture has just one great big piece, 1. Great. All right, so what can I do here? I see the plus 1s are going to cancel. I see the b's are going to cancel. So I see an I plus a t minus an ei equals a 1. So let me just make this ei is going to be I, or t plus I minus 1. I think I did that correctly. All right, great. So there's a formula for the number of interior edges. Let's put it in this formula at the top. So that tells me, but I'll change color, I'm so excited, that 3 times the number of triangles will be double EI, will be 2 times the number of triangles plus 2 times the number of interior dots minus 2 plus B. And, 3t, 2t, subtract 2t from both sides. The number of triangles is forced to be twice the number of inside dots plus the number of outside dots minus 2. There it is. Pure arithmetic of these counting formulas tells me the number of triangles is indeed fixed. If you draw B dots on the outside, draw a B-gon, and put I dots on the inside, you are forced to have double I plus B minus 2 triangles. And let's check here. How many triangles do I have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. I have 15 triangles there. We'll see. Double that. Double that is 10. Plus that is 17. Take away 2 is 15. Bingo. Beautiful. Number of triangles is indeed fixed. In 1899, Austrian mathematician George Pick discovered something absolutely delightful about polygons drawn on square lattices of dots. Here's a square lattice of dots. Every 4 dots are the vertices of a square. And let's assume that the area of the basic square here is 1 square unit. Great. And George Pick discovered something about the area of any polygon drawn with corners on those dots. It goes as follows. He says all you have to do is count dots. Count the number of inside dots. We'll call that I. So he discovered that the area of the polygon is going to be match the number of inside dots you've got, and also count the number of boundary dots you've got, how many dots are on the boundary, and divide that by 2, the number of boundary dots divided by 2, and then subtract 1. The area of this polygon is sure to match that count right there. Whoa, whoa. Now in our example, we seem to have, 4 inside dots. I can see 4 of them, 1, 2, 3, 4. And the number of boundary dots seems to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So apparently the area of the polygon on the board right now is going to be 4 plus 6, take away 1. Area is 9. And check, the area of that thing is indeed 9. Whoa. Now we also have formulas for something about polygons with dots floating around. Namely, if I subdivide this into triangles, if they let me do that, we have a formula for the number of triangles we are sure to get. So here comes some triangles. This is good, this is good, that's a triangle, 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 triangle. Okay, there's some triangles. And we know the number of triangles has to be given by, well, what we had before. Double the number of inside points plus the number of boundary points, take away 2. Now look at these two formulas. They're remarkably similar. Whoa, whoa. In fact, I could see each and every triangle here has area half. That has area half, that has area half, that has area half. Oh, except for some triangles are a bit weird. Look at this triangle. It's only got a dot on each of its 3 corners. Is that area also a half? Wow, here's another weird triangle. Is that triangle also area half? Well, I claim each and every basic triangle in that picture does indeed have area 1/2. So here's the number of triangles, each of area half. Then we conclude the area of this thing must be t times 1/2. That many groups of 1/2. Well, for the area, which would be half of this plus half of this minus half of that. And there's Pick's formula. Whoa. So actually, our formula is a derivation of Pick's formula, provided we are sure that each and every basic triangle like this one, with just dots on each of its corners, has area 1/2. So we better prove that. Okay, here's one of these basic triangles. It's on a square lattice, each corner's on a dot, and they're the only dots on the triangle. None inside, none on the edges, just on the corners. And we need to prove the area of this thing is 1/2. 1/2 of a basic unit square. All right, we don't know that yet. Let me just call the area of that triangle alpha, alpha square units. So let's see if we can figure out what alpha has to be from this picture. Well, that triangle is very awkward and slanty, but I do see, actually, if I can, from symmetry, I can also draw the other half of this triangle, copy right there, that actually that triangle is half of a parallelogram. And what I like about parallelograms, let me draw it over here, is that with parallelograms, I can actually start tiling the plane. I can draw the parallelogram underneath, another one underneath that. I can draw one to the right of that, and so on and so on. So actually, I can use parallelograms to cover the entire plane. Grand and good. Actually, that really means I'm covering the entire plane with these triangles. Let me draw the lines for the triangles. So there's all the triangles. That goes. So these triangles actually cover the whole plane. And of course, we've got all these grid points. There's a grid point, there's a grid point, there's a grid point, and so on. And in fact, all the grid points of this picture actually do appear in this triangle. This grid point will be somewhere on that picture if it covers the whole plane, but it won't be at the inside of a triangle. It's never on the inside of a triangle, never on the edge of a triangle. It must be at the corner of a triangle. So actually, every possible grid point does appear in this picture. All right, then my picture's a bit wonky, it's not very good, and I'm missing things. All right, okay, no worries. What do we notice here? I do notice some things. I do notice that every grid point was actually definitely covered by 4 parallelograms, which means it's actually covered by 6 triangles. 6 triangles cover each grid point. Yes, 6 triangles cover each grid point. Also, every triangle is associated with 3 grid points. Okay, now I'm going to do something weird. I'm going to divide the area of each triangle into thirds. So I don't know how to do it, maybe something like this. I'll draw lines maybe like that. Not very good. But I'm going to associate this third of area with that grid point there. I'll chop the area of this triangle into thirds as well, something like this, and give that grid point that amount of area. But for each triangle around that grid point, chop the triangle into thirds. I could do that, and actually now have, in a very bad picture, surround this grid point by 6 thirds of the area alpha. All right, so not very good picture, but hopefully you get to see what I'm doing here. Basically, I can surround this grid point with 6 thirds of alpha. 6 thirds of alpha is 2 copies of alpha. There's 2 alpha amount of area around this grid point. And I can do the same thing around this grid point, basically the same thing around this grid point. Actually, I can surround each and every grid point of my grid by 2 alpha worth of area. Okay. So I can naturally associate with each grid point a smear of stuff around it of 2 alpha area. And these all lock together and cover the whole plane. Now let's use that to my advantage, but let me work with an area I understand. But let me clean the board to show you the area I understand. Back in a moment. Okay, what I've got here is a square of dots. I understand squares, I understand the area. I guess I've done a 4 by 4 array of dots, but really it's in terms of side lengths, it's a 3 by 3 square. In area, so the area is going to be 3 squared. But let me not do explicitly 3. Let's say this is a b by b square of area. So I know the area of what I'm drawing on the board right now is b squared. The area is b squared. All right. Now what I'm going to do is cover each grid point with that 2 alpha of area. And how many grid points are there? Well, if this is b steps, that means there's b plus 1 grid points. It's actually b plus 1 by b plus 1 b plus 1 by b 1 grid points in that picture, b plus 1 squared. Each grid point is going to be covered with 2 alpha of area. Cover that with 2 alpha of area. Cover this with 2 alpha of area. Cover this with 2 alpha. Cover each and every grid point with 2 alpha of area. So very messy. Cover everything with 2 alpha of area. And that's going to cover absolutely everything. This is grand and good. It's very tedious watching me do this, but there we are, all my grid points. The whole thing is covered with 2 alpha of area. So I could say that the area is also b plus 1 squared grid points, 2 alpha of area of each one, 2 alpha times b plus 1 squared, except I've got all this excess area, went over my square, minus some excess area. All right, okay, so there are 2 forms of the area of that square, the area I know. Okay, that's not very helpful. All right, but it does give me a form for what the excess actually is. It tells me the excess is actually going to be given by 2 alpha b plus 1 squared minus b squared. So there's a form of the excess area outside of my lovely original square. Now, remember, each of these regions of area is made of 6 copies of that triangle. In fact, 6 copies of 1/3 of that triangle. So actually my picture's going to be very pointy. I've got like all these little pointy bits of triangles. So it's really about pointy bits of triangles coming off the edge here. Okay, let's make my picture really impossible to look at. All right, so the question is, how far could these bits of a triangle point out? I guess I need another sense of the size of this thing. Okay, here's a triangle. Let's call its longest side length. Longest side is going to be of length L, say. So if this is like a third of a triangle whose longest width is L, this is going to be totally within 1/11 outside of a distance of 1L from my big square. So L, L. If I do a border that's L wide around my original square, none of these pointy bits will actually reach that border. So all my excess area is sitting within this border strip, L by L by L beyond that B by B square. Which means I've got a formula for bounding that area. All right, so, okay, remember this notation because I need some more space in my messy, messy picture. So we know that this excess, so, okay, the excess is something. 0 is less than or equal to excess. Great. And it's going to be within the area of that strip. That's a B plus L plus L. B plus 2L squared area minus the inner square. I know it's going to be at most B plus 2L squared minus inner area is B squared. So there it is. The excess is bounded by that formula. And there's a formula for the excess. Where am I going with this? Well, I need more space, So let's see if I can erase that part I don't need anymore. I need a formula for the excess. So let me keep it on the board for the moment. Let me change colors so I can see it. But what we're saying right now is that 0 is less than or equal to this formula. Let me expand it out. 2 alpha b squared plus 4 alpha b plus 2 alpha minus a b squared. And that's going to be less than or equal to, expand that one out, a b squared plus an 8bl, I believe. I'll probably get that wrong, plus 4l squared minus a b squared. All right, okay, so I've got this crazy formula. Where is James Tanton going with this? Well, he's trying to see what alpha is, remember. We want to know what that actual area of the triangle is, but I'm claiming there's got to be some lovely information in here. For example, I'll get rid of b squared and b squared. So what I'm really saying right now, I'll go back to pink. 0 is less than or equal to 2 alpha minus 1, there's all the b squareds, plus a 4 alpha b plus a 2 alpha, and that's going to be less than or equal to b squareds cancel, 8lb plus a 4l squared. All right. Okay. This is great. Probably doesn't look great, but it actually is great. Because I'm seeing a b squared there. All I'm seeing there is a b and a number. All right. I never specified how big or small I wanted b to be. I could make it any number I like. I might make it 1,000,000. In which case, this is saying something times 1,000,000 squared. That's really huge, like 1,000,000,000,000 or something, plus something just in the millions. That's kind of trivial compared to that. Has to be something less than or equal to something again in the millions. Something in the trillions plus some little fiddly stuff has to be less than or equal to something in the millions. That seems problematic. The only way that can be resolved is if that thing isn't there. Namely, this term is 0. All right, this is looking good. It doesn't, if you really want to clinch it mathematically, how would I argue that? I guess we can let b be any value we like. Let's see if I can clean this up. Let's take that inequality, just to be mathematically precise, let's now divide through by b squared. All right, so that's telling me 0 is less than or equal to this number, 2 alpha minus 1, divided by b squared, plus 4 alpha over b, plus 2 alpha over b squared. And that's less than or equal to, hopefully I'm still on the board, 8l over b plus 4l squared over b squared. All right. This is looking very calculusly, looking like very squeeze theorem type stuff. But let b gets bigger and bigger and bigger. That's going to stay as 2 alpha minus 1. It's still bigger than or equal to 0. This thing is going to go to 0. This thing is going to go to 0. Something divided by b, as b gets bigger and bigger, wants to get really close to 0. Something divided by b squared wants to go really close to 0. Wants to go less than or equal to something that's really close to 0 plus something that's really close to 0. This quantity here wants to be stuck between something that wants to be stuck between 0 and something else that's getting really, really close to 0. This quantity has to be 0 itself. We need 2 alpha minus 1 to be 0. Alpha has to be 1/2. The area of this triangle has to indeed be 1/2. Whoa, that was crazy, but there it is. And of course, this argument would apply to any triangle of this nature I draw. I can see it's half a parallelogram. Those parallelograms will cover everything. Off we go, exactly the same argument. The area has to be 1/2, no matter what. Amazing. Okay, time for some extra fun. Instead of doing polygons on square lattices, let's talk about shapes on triangular lattices. Here's an equilateral triangular lattice. Every region is an equilateral triangle. And let's assume a basic equilateral triangle is area 1 square unit. All right, here's your challenge. Prove that you draw a triangle that connects 3 dots so that they're the only 3 dots on the triangle. Let's do something like this. Maybe go up over here, and then maybe to this one, and there's a triangle. Yeah, it's got 3 dots on it, only appearing on its corners, no dots inside, no dots on its edges, only the 3 corner dots. Can you prove, in fact, follow the techniques we did before, that the area of this triangle matches the area of this basic triangle? It's 1 square unit of area. Because if you've done that, then you're all set for a version of Pick's formula for triangular lattice polygons. And it'll be this. Let's draw a polygon that connects dots on this lattice. Something like this will do. I don't know, something. There we go. There's a polygon. We know if we divide that into triangles of this type with only 3 dots on its boundary, so let me do that right now, we have a formula for the number of triangles that will be so created. So let me quickly do this. Let's do a strange one like that, like that, like that. Okay, there we go. I'll just do a little sort of hexagon pattern for that. I think that's it. All right, great. Because we know the number of triangles is going to be given by number of triangles is twice the number of inside points plus the number of boundary points minus 2. But if you succeeded in proving that each of these triangles is indeed of area 1, then the number of triangles matches the number of units of area within that polygon. In which case, this form is really reading right now, the area of this polygon is twice the number of inside points plus the number of boundary points minus 2. And that would be a version of Pick's formula for polygons drawn on a triangular lattice. Whoa, whoa, whoa. But we need to know for sure that's area 1, but I bet you can do it, and voila, look what we got.